bases. So, what did we talk about last time? Acid and bases, I imagine. So, remember again, acids are, again, anything that will produce H plus ions in solution. Again, H plus and H3O plus are, which is the hydronium ion, are essentially the same thing when we do acid and base chemistry. So as I mentioned, I think last time as well, anywhere really in either formulas or even equations that you see H plus, you could exchange it out for H3O plus, or vice versa. If you see H3O plus, you could exchange it out for H plus. Again, the reason you do get H3O plus is a lot of times people, when they're dealing with acids, will kind of use water as part of the equation, and that's what really produces the H3O plus. But they're essentially the same thing here. Bases, again, are substances that can produce hydroxide ions in solution. Remember that when we're talking about these, we were talking about the ability to produce free floating H pluses in solution or free floating OH minuses in solution. And again, not attached to anything, kind of freely floating around. And as we talked about, and as we will see, again, that ratio of basically how much H plus you have to OH minus, or vice versa, OH minus to H plus, will determine whether or not the solution is going to be acidic, basic, or neutral. And again, that's how much of that free ions are floating around in that solution. Again, not attached to anything. This was sort of the Arrhenius definition of an acid and base, sort of a broad definition. A lot of times when we do talk about acid and bases, most people focus in on the Bronsted-Lowry definition. And the Bronsted-Lowry definition of an acid is a proton donor. And once again, what that means, it is somebody that will basically transfer an H plus to some other substance. Now, it's important, as we talked about, that it's not just the hydrogen that gets transferred, but it's also the plus as well. Thank you. Okay. So again, it's not just the hydrogen, but again, also that plus, which affects the actual charge on what is losing the H plus and what is gaining the H plus. So remember that if you lose an H plus, which is really a proton, and you basically have more electrons than protons, so you become more negative. So if you're the acid in this case of the Bronsted-Lowry definition, you're going to lose that hydrogen and the plus charge, which means that you actually become one more negative than you started with. If you're accepting the H plus, then you're obviously accepting the hydrogen and the positive charge, and you actually become one more positive than when you started from. And where that H plus goes is obviously the base, which is our proton acceptor. And again, it's going to accept that proton. The sort of reality of the Bronsted-Lowry definition, as we talked about, is we will have acids on the left-hand side of the arrow and base on the left-hand side of the arrow are reactants, and they will make partners on the other side, which are known as conjugate bases. And the base will have a partner on the other side, which is the conjugate acid. And basically the idea here is that acid will donate that hydrogen over, and the only difference, as we talked about, for these guys to be considered conjugate acid base pairs is, again, that 1H plus difference. As you go from the acid to the conjugate base, it has one less H plus because it gave it away. And as you go from the base to the conjugate acid, it has one more H plus. Now, when we do this, there are certain things, for example, that could act as an acid or a base, and those are known as amphoteric substances. And water is such a substance, and water will actually set up an equilibrium reaction with H plus and OH minus. And we could write an equilibrium constant for this, which is known as Kw, which is the concentration of H plus times the concentration of OH minus. And that equals, at 25 degrees, 1 times 10 to the minus 14. That's sort of a constant number, pretty much. That's usually the number that you use for kW. Reality, though, is it does change with temperature, but you probably won't come across anything like that. So that's usually sort of a constant in this case. When we do those brackets, as we might have talked about, that does represent molarity usually, and concentration really is what it represents. And again, usually that is molarity, which is our moles per liter. So we can use this, and you could also, as I mentioned before, as we talked about, substitute out the H plus for H3O plus, and it's exactly the same thing here. It's the exact same formula. It works the exact same way. Again, H plus, H3O plus is really the same thing. You could use that to solve for either the H plus concentration if you have the OH minus concentration, which would be 1 times 10 to the minus 14 divided by the OH minus concentration. Or if you have the H plus concentration, you could get the OH minus concentration by taking 1 times 10 to the minus 14 divided by the H plus. You definitely, as we talked about, want to make sure you're using your exponent button when you punch these in. Otherwise, you will find yourself off. And if you can figure out the H plus concentration and the OH minus concentration, you can use those to determine if the solution is going to be acidic, basic, or neutral. So if the H plus concentration is greater than the OH minus concentration, that basically means the acid part is greater than the base part. That would make this solution acidic. If the H plus concentration equals the OH minus concentration, then they actually both will equal 1 times 10 to the minus 7 molar, and that would be neutral in that case. And if the H plus concentration is less than the OH minus concentration, that means the base part here is greater than the acid part. It will be basic in this case. So that is one way that you can sort of figure out whether or not a solution is acidic. The other important thing is when you are comparing those concentrations, as we talked about, remember that they typically will have negative exponents. And when you look at the negative exponents, the smaller negative exponent is the larger number. So sometimes people just look at the number, not the negative part of it. And that is an important thing to look at. Most of the time, though, we do roll with the pH scale as sort of what we look at in terms of trying to determine if something's acidic, basic, or neutral. It runs from 0 to 7 to 14. Again, below 7 is acidic, above 7 is basic, and really right dead on 7 is neutral. And that's because that is when they both equal each other. And if you calculate the pH of a solution at that point, it will give you a pH of exactly 7. So technically speaking, 7 is really neutral. As you go from 7, which is sort of your midpoint of the scale, and head towards 0, you are becoming more acidic. And as you go from 7 heading towards 14, you're becoming more basic in that case. You can calculate the pH by taking the pH is equal to negative log of the H plus concentration. Once again, this is the same as pH is equal to minus the log of the H3O plus concentration. So again, they are the same thing. It also tells you in the actual name what you need to calculate it. pH means that you need the hydronium concentration or the H plus concentration, and that's what you should use. We also talked about the importance of punching this into your calculator correctly. So just a reminder, if you have that display calculator, you will punch it in exactly the way the formula is written. You would use your negative button, you use your log button, and then you put the number in probably with your exponent button, and then hit equals. If you have the non-display calculator, as we talked about, you pretty much with this one and all these sort of equations here in this chapter has to kind of work backwards when you punch it in. You kind of has to work in this direction, which means that you would actually put the number in, probably using your exponent button. You would then hit the log button, and then you would hit the negative button. So again, you kind of have to work backwards depending on which one that you have. Any questions on any of that there? All right, so this is about where we left off. So as we talked about a little bit last time as well, again, there are a couple ways that you can measure the pH of a solution. As I mentioned before, a pH meter is an electrode like this, has like a little glass guy at the bottom. and you put it in there and it essentially measures how much H plus ions are floating around in that solution. And the nice thing about a pH meter is it actually does just give you an actual number there. It's pretty accurate because again, you typically will calibrate it before, and a lot of times you'll calibrate it as with a pH of 4 solution, a pH of 7, and a pH of 10. So you get a little calibration curve over the entire pH scale. And then it measures the voltage of your solution. Kind of like what we did in lab there. You could also use some pH paper and try to match up the color the best you can to whatever it is. Not as accurate as you probably found out when you did the experiment. You're like, kind of looks like both of these colors. I'm not really sure which color it is. So that's another way you can do that. Obviously, as we also talked about, litmus paper, which does not give you the pH, but again, will tell you if it's acidic, basic, type of solution. And again, if litmus paper turns red or stays red, it usually is acidic. And if it turns blue or kind of stays blue, it is basic. So that's another way, again, not getting the pH, but allowing you to know whether or not your solution is acidic, basic, or neutral. How do you know when you, for example, look at an equation if you would expect it to be, for example, acidic, basic? You could do that by very simply when you look at the equation on the product side, if you see basically any H plus by itself or H3O plus, it's probably a pretty good bet that that solution is going to be acidic. Now, same thing if you kind of look on the product side of the arrow and you see hydroxide there by itself, or any type of hydroxide, it's probably a pretty good bet that it's going to be basic. So again, in a chemical equation, sometimes, you'll see H plus or H3O plus on the product side or OH minus on the product side. And that's usually a fairly good indication that, a solution is either acidic or basic. Here is our pH scale, and again, we have our 14 here, which is our strong base, sodium hydroxide. We got our 0 pH there, which is our hydrochloric acid. We have some common acids there, like vinegar, acetic acid we use in that titration experiment, lemon juice, your stomach acid. A lot of cleaners and stuff like that is basic in terms of that. Here we have pure water, which is 7. If you took the pH of water that it was, out for a while, would it be 7, the pH? Odds are it will not. It will probably be more in that range right there, a little acidic. And that's because if you leave water out, a lot of times it will pick up some CO2 from the air, make a little carbonic acid, and that tends to increase the H plus concentration a little bit. And what that does is make your pH a little bit more acidic. So sometimes people are surprised if they check the pH of water, especially if it's been sitting out for a while, and it's not like a pH of 7. It's usually slightly acidic when you do that. That's why if you really want sort of pH of 7 water, sometimes when people used to do titrations years ago, they would make you take your water and you would actually boil it. And that would release the CO2 back out of the water and bring the pH back up to more like a 7 and stuff like that. Nowadays, the buildings are pretty tight and sealed pretty good, so they don't make you do that anymore. But years ago, in these older buildings with windows, when you do like a titration experiments like we did, you would make your sodium hydroxide and kind of boil out the water and stuff like that to bring the pH back to 7. Now, we did touch upon this as we were doing, I think, one of the last examples last time, and there is obviously similar scales to pH, and some of you might have calculated the pOH in that last problem that we did last time on the board, and that is when you have the OH minus concentration. So the pOH, again, the name gives you an indication of what you need. pOH means that you do need the OH minus concentration here to calculate it. It is pretty much the identical calculation to pH. Take negative log of the hydroxide concentration. So we put our pH in there with it, minus the log of our H plus. Once again, the nice relationship between these two is what we see here on the bottom we talked about, and that is that the pH plus the pOH is equal to 14. So what this gives you is a little bit of flexibility in terms of your calculations. There are a couple of ways you could get to the answer. So for example, if you were given hydroxide concentration like we were in that last problem that we did, the other day. You can very simply calculate the pOH, and if you're interested in what the pH is, all you have to do is take 14 minus that number, and you will actually get the pH without having to do some other calculations. You could, as well as we did in that example, you could still use your Kw to get the H plus concentration and then go into the pH equation. They both should give you the same answer. So with that in our Kw that we saw before, it does give us a variety of ways that you might be able to solve a particular problem. A reminder, though, that as I mentioned, there is only one answer to that question. Is it acidic, basic, or neutral? And again, very commonly people will calculate the pOH and also calculate the pH in the same problem. And again, give like it's acidic and basic because one's above 7 and one's below 7. I would recommend highly that most people, if you want to determine acidic, basic, or neutral, I would look at the pH scale, as that is pretty much the one most people have in their head. And that is the one that we saw a second ago, where that is acidic and that is basic. And obviously that is neutral. Oops, that's the pH. That's the pH. The pOH scale does also run through the same numbers, but it is opposite. So a low pOH there is actually going to be basic, and a high pH will be acidic. So if you have a low pH, you will have a higher pOH, and they both will mean that they're acidic, and vice versa there. So you do want to make sure that you look at the right thing, and I, again, would always kind of look at the pH. Can you have something above 14 or a negative sort of pH? The answer is yeah, you can. I think you might even have one on one of those post-lab questions on the lab that we did the other day. And that's what's sometimes referred to as a superacid. If you take like the pH equation there and you plug in like negative log of like a 12 molar solution, you'll get a negative 1.07 pH. And that's because it's very, very highly concentrated. It's like a superacid in a sense. So it is possible to actually have like a negative pH. In most cases, you probably won't unless you have something that has a really high hydrogen concentration. Most of the time it will stay on the pH scale, but it is technically possible to do so. The other thing we talked about when we calculate pH is also significant figures, right? So a reminder that when we do calculate something like pH or pOH, the number of decimal places in your pH or pOH answer should have the same number of decimal places as the significant figures there are in the concentration value. Now, so these are a few ways that we could calculate sort of our acidity or basicness, but there are a couple other calculations that you can do that are important. So if you are actually given the pH value, from the actual pH value, much like the name implies, you can get directly from that the H plus concentration. So if you are given the pH and you want to know what the H plus concentration is, the H plus concentration would be the inverse log of the negative pH. I would say on most people's calculators, when they do an inverse log, it will pop up a 10 and a caret, and then you want to make sure you go negative pH on that. Now, you could also, if you have the pOH given to you, maybe not surprisingly enough, from the pOH directly from that number, you could get the OH minus concentration. And it is pretty much the same calculation. It's going to be the inverse log of the negative pOH. That will get you a 10 and a caret, negative pH. Where do you find that on your calculator? I would say on most people's calculators, top left corner, there's a second button or a shift button, one of those buttons. And then you should have a log button somewhere that says like 10 to the x, also known as what a lot of people use for scientific notation incorrectly, which is why you do not want to use that for scientific notation. You want to use your exponent button, otherwise you're going to be way off in these calculations. So usually you need to hit a shift or a second in the log button. And again, that usually will pop up on your display a 10 and a caret. You want to, again, make sure that you do the negative. So if you have a display calculator, you again are going to hit it in exactly the way it's sort of the formula. You would do either your second button or your shift button. You would do your log button. You would then do your negative button. And then you would do your pH or POH value in there. And then hit equals. If you have a non-display calculator, just like the other equations, you need to work backwards. So you will actually start with either your pH number or POH number and just pop that in there. And then you will actually hit the second or shift button. You will then hit the log button. Actually, no, you will not. I'm sorry. You actually need to, before you do that, hang on a sec. I forgot one little important step there, probably on most people's calculators. All right, so you'll put your pH or POH number in there, and then you'll actually make it negative first. There we go. And then you will do a second button or shift button and the log button. So you got to make it negative before you do that. And then you should be in good shape. So that usually is how you'll punch it in, depending again on your calculator. Once again, if you don't remember which one you have, hit log. And if it says log, you have a display calculator. If it says error, you have a non-display calculator. Any questions on any of that there? All right, so let's try some maybe here. All right, so for each of these, let's calculate everything just to make sure our calculators work. The OH minus concentration, the pH, the POH. Is it acidic, basic, or neutral? For the second one, let's calculate the H plus concentration, the pH, the POH, and again, is it acidic, basic, or neutral? See, we'll start with the first one here. So we have the H plus concentration. And since we are looking really for everything, you could really start in one, two things. So from the H plus concentration, you definitely can directly get the pH from it. You could also use Kw if you wanted to get the OH minus concentration using Kw or just a pH equation. So it really doesn't matter which way you want to go, but I'm going to go pH first. So pH here is equal to negative the log of the H plus concentration. So once again, we're going to put that in, negative log 3.6 times 10 to the minus 9. And that will get us a pH here of, looks like 8.44. Once again, in terms of significant figures and all that, our concentration had 2 sig figs. And again, that's not how many sig figs in the pH, but it's how many decimal places here. So that would be 8.44 in this case. Now, at this point, it also opens up a little bit of options. Since you now have the pH, you can very simply use the pH plus the POH is equal to 14 to get yourself to the POH. So that means the POH would be 14 minus the pH. So we'll just take 14 here minus our 8.44. And that's going to get us there a 556, it looks like 5.56. Now, at this point, you also have a couple of options. You can go back to Kw like we did before if you wanted to. So you could do the OH minus concentration will equal 1 times 10 to the minus 14 divided by the H plus concentration, which would be 1 times 10 to the minus 14 divided by our 3.6 times 10 to the minus 9. And if you do that there, I'll get you probably like a 2.8 times 10 to the minus 6 molar. You also could, because you have the POH, we could use the POH and go that the OH minus concentration is equal to the inverse log of the negative POH, which again, display calculator, second log negative and 5.56 and equals. Non-display 5.56 negative second and log. And whichever way you go on that there, negative 5.56. Gonna get us a same thing here, 2.8 times 10 to the minus 6 molar. So as you can see, it doesn't really matter which way you go at it. You can get it there. You also obviously could have got the OH minus first using KW. And then you could have got the POH by doing what we did before as well. So again, you do have a variety of sort of options as to how you can kind of get to whichever way you want to go. They all really, again, should give you the same answer. Maybe slightly off, depending if you did a little bit of rounding, but it should be pretty darn close no matter which way that you go. Any questions on that there? Clearly, at this point, this solution would be basic. Yeah. And again, I'm looking at the pH value only. Again, not acidic and basic together. Any questions on any of those calculations there? All right, take a look at the next one there that we have, which was this one, I think. In this case, we have the OH minus concentration, which again, since we're looking to solve for everything, does give you a variety of ways. You could use KW to get the H plus concentration directly from that, as I butchered it out there. H plus, there you go. Clearly as well, you could go right into the POH equation, and that's what I'm going to do in this case. I'm going to go right into the POH equation and calculate that first, since it doesn't seem too difficult. So we'll go negative log of 9.2 times 10 to the minus 2, and that's going to get me here. Looks like a 10.36 POH. Again, probably the easiest move at this point is just to go pH plus POH equals 14. Do a little subtracting of 14 to get yourself there to your pH value. And at that point there, looks like a 1 point. I feel like I wrote 10 wrong there, huh? When we come to scientific notation, I read that really badly. All right, I'm going to try that again. All right, so minus the log of 9.2 to the minus 2. How about a 1.04? It's kind of like the same numbers, but better, I suppose this is right. All right, 1.04. There we go. And obviously here, I'd be subtracting 1.04. There we go, 1.04. There we go. All right, so 14 minus 1.04 going to give us a 1296 here. And at this point, since we do have the pH, we could get our H plus concentration. Again, I'll do this way, inverse log of the negative pH. Again, on your calculator, probably going to look something like this when you pop it into your display. And that would get us here. We'll call it 1.1 times 10 to the minus 13 molar in this case. Again, you could have used KW and got that same number. And remember that as we go backwards, I have 2 decimal places here. Should give me 2 significant figures as we go backwards. So again, you want to make sure it works both ways. 2 sig figs as you go backwards. And obviously here, we're going to go basic on that there. So that's going to be basic in terms of our pH here. Any questions on either of those 2 there? All right. So let's go then and look here. Something. All right. So the pH of this solution is 5.67. What is the POH? And just to make sure, OH minus concentration, H plus concentration. And again, is it acidic, basic, or neutral? Okay, so here we do have the pH. So obviously very easily we could get the POH. Again, we're just going to take 14 minus our pH value. and that'll give us 14 minus or 5.67. And looks like here 833. At this point, you can start with either one here. We'll go H plus concentration is equal to the inverse log of the negative pH. Again, when you pop that into your calculator, it probably looks something like this on the screen, hopefully. And if you do that, you will end up with, looks like, about 2.1 times 10 to the minus 6. Remember, you do need units since it is molarity here. At this point, you could use kW if you wanted to get the OH minus concentration, or since you also have the POH, you could do pretty much the same calculation with the OH minus concentration, which would be the inverse log of the negative POH, 10 negative 8.33, and looks like maybe a 4.7 times 10 to the minus 9 molar. Once again, here we have two decimal places taking us back to two significant figures when we do the concentration. This is obviously from the pH value here that is less than 7, so that is going to be acidic in this case. Any questions on any of those calculations there? All right, try a couple more here. All right, pH is 3.14. What's the H plus concentration? So here again, we have the pH. And once again, as I mentioned, the name does tell you what you can get directly from it. So pH means you can directly, again, get your H plus concentration by doing that inverse log of the negative pH. So once again, here you would pump into your calculator your second button, your log button, your negative, and 3.14 and equals. Again, if you had a non-display, you would go 3.14 negative second log, and should pop something again up on your screen. Looks something like that probably in most cases. And that's going to get you here. If I put in the right number, would be good, I suppose. Looks like 7.2 times 10 to the minus 4 molar in this case. By the way, again, it may not give it to you in scientific notation. It may give it to you, obviously, in decimal form, and you can put it into scientific notation if you want. Or you can leave it in decimal form, just the right number of significant figures. If you leave it in decimal form, you might miss some zeros or something. But again, two decimal places, two significant figures going in that direction. Yeah. Any questions on that there, on that one? All right. One last one here. POH, what is the OH minus? Okay, so again, here we have the POH telling us that we can get directly from it the OH minus concentration using our formula here. Good news is it's really the same formula regardless of which one you're doing. Again, going to do a basically a 10 and a caret minus 5.67 in this case. And that's going to get us here, not that, minus 5.67. A 2.1 times 10 to the minus 6 molar in this case. Any questions on how to calculate pH, POH, H plus, OH minus concentration? Again, you do have a variety of ways you could perhaps do it depending on the information given to you and depending on the direction you go as to what you calculate sort of first. Again, there's really no wrong way as long as you punch it in correctly. Any questions on that there? All right. Then the next thing we're going to talk about is actually a pH of a strong acid or a strong base, really. We'll get into that in just a second. But so up to this point, and a lot of times you are given a more sort of generic, like, what is the pH of if the H plus concentration is this, or the OH minus concentration is this. Now, in some cases, you may be given an actual formula for an acid or a base and asked to calculate the pH. And it does sort of work the same way. So this is similar to kind of what you did in second part of that acid-base experiment. So if we have a strong acid like hydrochloric acid, what we know about a strong acid is when it is in water and it's sort of dissolved in water, it completely ionizes or breaks apart into ions, which means this hydrochloric acid will essentially 100% break apart into H plus ions and Cl minus ions. That means really when you look at the beaker and if you throw your HCl in there, you will have, again, none of those units of HCl still together. You will have basically just ions running around. And once again, as we talked about last time, that is why this is considered a strong acid, because really all it has to do is go for a swim and it will generate a lot of free H plus really quickly in that solution. And as the H plus concentration goes up, the OH minus concentration goes down, and also the pH goes down because there's a lot more acid part in the solution than there is base part in the solution. Now, a reminder that there is that list of strong acids, which frankly you should be aware of because it does make things somewhat easier. Hydrochloric acid is obviously on that list. Nitric acid is on that list. Perchloric acid is on that list. Sulfuric acid, hydrobromic acid, and hydroiodic acid. So these 6 sort of strong acids are a good list to know because if it's an acid and it's not one of these 6, it's probably a good chance it's a weak acid. So it's a good process of elimination. If you just know these 6 and it's not one of the 6, then you're probably dealing with a weak acid, which is a little bit different in terms of how you get the pH, which we don't talk about here. You would talk about a 1B, but it's a much longer calculation. By the way, since we are going to talk about bases as well, strong bases are usually found there in group 1 and 2 on the periodic table, with those guys that have hydroxide in it, like sodium hydroxide, potassium hydroxide. These are some strong bases. Pretty much if you go to the periodic table there and you find like lithium and you go down to potassium, you hang a right hand turn there to calcium and kind of go down. Any of those guys in group 1 or 2 that has hydroxide in it, most likely will be a strong base. So again, that's why, again, as we talked about, group 1 and group 2 are the alkaline metals, the alkaline earth metals. Alkaline means basic, and that's where a lot of our strong bases basically come from. A lot of our acids actually come from nonmetals, and nonmetals together on the top right of the periodic table is where we get a lot of those guys. So if you have a strong acid and you want to figure out what the pH is, obviously the most important part of this is the H plus concentration, because that is technically what we would put into our pH equation, right? Our formula here. So we need to find, again, a way that we can figure out this. And we could do what we talked about when we did concentrations, which is sort of molarity of ions, and kind of like a mole to mole relationship. For every one of these, you get one of these, which means whatever this concentration will be the same as the concentration on the other side for the H plus, because it is a 1-to-1 relationship. So for example here, if we had 0.1 molar hydrochloric acid and we wanted to determine what is the pH of that, we could do our breakdown here of basically our acid dissociated into H plus and Cl minus. And because this is 0.1 molar, as I just did a second ago, it is a 1-to-1 relationship between that, which means if you want the concentration of the H plus, you would take 1 times the 0.1 molar, which would give you 0.1 molar. By the way, you could do that for the chloride, although we're not really interested in this case, it is 1-to-1. And for the chloride, it would also be 0.1 molar of chloride ions in that solution. Again, not really important for the pH, but that's how you would get it. A reminder that the long version of that calculation is this. You take your 0.1 molar, which is moles per liter of HCl. You basically do a mole to mole relationship like we just talked about, which is for every 1 mole of HCl, you get 1 mole of H plus. The moles of HCl cancel, and you end up with 0.1 moles per liter H plus, which is 0.1 molar H plus. So that's really the long version of the shorter calculation of figuring out the concentration of the ions. It's a lot of times easier and quicker just to basically multiply by the coefficient that's in front of the ion, and that will give you the correct concentration for that particular ion that you're looking at. Or again, you could do the calculation on the bottom, more of a dimensional analysis, stoichiometry, mole-to-mole relationship, and you could get it as well. Any questions on that there? So really at this point, since we do have the concentration of H plus, we can go into our pH equation minus the log of the H plus concentration. And that's going to give us negative log, in this case, 0.1 molar. And that's going to give us a pH in this case here of basically a pH of 1. And in this case, we would want to go 2 decimal places as our concentration had 2 significant figures in this case. And that definitely is acidic, right? Any questions on that there? Now, we could also do something very similar if we were dealing with a base and we want to know what is the pH of the base. So, for example, if we had a strong base, say like potassium hydroxide or something of that nature, I'll go here. So let's just say we had the same guy, but it was 0.1 molar potassium hydroxide, right? And again, here, the potassium hydroxide is a strong base, which means it will 100%, like our strong acid, dissociate or break apart in solution into K plus and OH minus. And when we look at this, in terms of the pH, what's important here is the OH minus. And the OH minus here is important because it will allow us to get to the pH, but it will not directly allow us to get to the pH like it did with our strong acid. We would first, when we get the OH minus concentration, could get to the pOH, and then we could get to the pH. So there is sort of a middle step in this calculation because you have the hydroxide concentration and not the H plus concentration. It will basically kind of work the same way. We will go 0.1 molar here. Again, the hydroxide is the important part. It's a 1-to-1 relationship here. That means basically we're going to take 1 times 0.1 molar, which for the hydroxide concentration will be 0.1 molar. Again, because it's hydroxide, that does not get us the pH, but it gives us the pOH, and that's going to be negative log of the OH minus concentration, negative log of our 0.1. That is going to give us, again, a pOH of 1. We can then get to our pH value by taking 14 minus our pOH, and that would get us 14 minus 1 here to give us a pH of 13. That definitely is basic, which is what we would expect since this is a strong base. We would expect, obviously, a basic pH here. Question on that there. Okay, so I think what we're going to do is